Okay, good morning, everyone. So today will be the last lecture. So I plan to finish the BJT, and then if the time is allowed, we will also to quickly review the concept of the JFET. And of course, today most important is that we will share the result for the midterm exam, and also we will just quickly go through for the final exam, the typical scene for final exam on this Thursday evening. Okay, so last time we have already mentioned that the related to the bipolar junction transistor, we have 4 different operation region, and the most important is under the operation of the forward active operation mode. So in this case, we will bias in the base and emitter under the forward bias, and we will bias the base collector under reverse bias. So when we consider the forward and reverse bias between the BE and BC, so we can have the band diagram that show me here, because due to the forward bias, so the barrier is reduced. But because of reverse bias, the barrier is increased. But at the meantime, once electron is able to flow through the base, and then because of this very large reverse bias, so the electron can be accelerated and reach to this collector. So this is a basic operation, and we will have more details to explain the device operation for the BJT in today. So we have already shown this minority distribution plot last time. So the base emitter PN junction is forward bias. So this is forward bias. So we can expect that the electrons from the emitter are injected from the base to the emitter across this base emitter junction. So the electron from the emitter are injected. Because of this is forward bias, so we can expect that the electron can flow, because of, think about the typical PN junction or PN die under the forward bias, we start to have the current conducting. This is the same concept. In here we can consider this is a typical operation for PN junction, and this injected electron that will create an excess concentration. So as I said, this is electrons in the N region, but once injected into the P region, this electron become an excess concentration. Because of this P region, the majority should be the holes, but now we have the additional electrons being injected into this one, and therefore this will become the excess concentration of a minority carrier in the base region. And the base collector PN junction is reverse bias. As already mentioned, in this case, the junction is under reverse bias. So the base collector PN junction is reverse bias. The minority carrier electron concentration at the edge of a BC junction. So because of this is under the reverse bias, so ideally at this edge, we should have the minority carrier concentration should be ideally approach to the 0. So this one is ideally 0. Show me here. Due to the reverse bias in this BC junction here. So therefore we will have, because our original minority excess concentration is here, and we will force the minority excess concentration at this edge equal to 0. So that will create a very a high gradient here. So the large gradient in the electron concentration means that the electron injected from emitter will diffuse. So now we start have a diffusion in this region because of this large concentration gradient. And this diffuse across the base region into the BC space charge region, and where the electric field will sweep the electron into the collector. So that is due to here. So the electron will first to diffuse to this region, and then because right now in the BC we have the large reverse bias, therefore this carrier will be swept by the electric field. And then in the end to reach to the collector size. So that's a basic operation for the BJT. And then the width of base needs to be small compared with the minority carrier concentration length. So the width of base should be small. We will talk about later that from the equation or from physics, as long as this is getting small, of course our gradient will be larger, so our carrier can diffuse through the base and reach to the collector side. Okay, so that's a consideration of this NPN bipolar transistor. So let me illustrate how this carrier, how this electron from the emitter in the end to reach to the collector. So first of all, this is under the 4 bias. So 4 bias is easy. Just we can understand that the electron can start to across the barrier and reach to the base region because of the 4 bias. But now we will apply the reverse bias here. And one critical part is that under the reverse bias, this carrier concentration, the minority carrier concentration at this point should be 0. So in this case, we have a huge excess concentration at this region, but it must be approached to 0 at this location. Therefore, we will have a large gradient, and large gradient will create the diffusion, so that then the electron can start to diffuse. And then again, once reached to this region, because we are under the reverse bias of the base collector here, so therefore the electric field will help this carrier in the end to sweep to the collector, and in the end become the collector current of the of a 1 BJT here. And actually, although in here we use a minority carrier distribution plot, try to help us to understand. But if you think about a little bit to compare with the MOSFET, operational MOSFET, you will find out that actually the operation of this is very similar to the case of a MOSFET. So let's just try to plot a MOSFET, which we should be very familiar. So in the case of MOSFET, we have the P substrate, right? And then we have the source and drain. So we have the N plus, right? So if you try to think about only this region, this is exactly the same as a BJT, which this region is a NPN, right? So we have a NP junction here. We have the PN junction here. So this region is actually identical to our bipolar transistor. So therefore, think about how actually let me just finish the full schematic for the MOSFET. So we will have the oxide here. and then we have the metal. So again, try to concentrate on this region, and then you will realize that this region is exactly the same as what we discussed here, which we have the NPN as well. And then therefore the operation for the MOSFET should be very similar, not exactly, but has a lot of physics in common that compared to the MOSFET operation with BJT operation. So as we all know that under the MOSFET operation, first we have to apply the gate bias here, and then at the meantime we'll apply the VD bias. So with considering this VD bias, actually we are trying to put this junction as a reverse bias, which again is the same consideration below. So if you try to plot this junction, the depletion width of this junction, so then it's the same exercise that we have been done before. So once we apply the VD as an increase, actually we will extend our depletion region, right? So again, this depletion region is the same, has the same characteristic like in this way here. And we all knew that once we apply the gate bias, we will start to form the inversion charge in the channel as long as the gate bias is larger than threshold voltage. But because of our VD is increased at the same time, so VG minus VD is smaller, in the end that will start to make our channel is not uniform, which will become the triangular, right? That's because of due to the influence of drain bias. So then we will start to have a triangular shape of our inversion channels under the gate. And again, we start to consider we have an electron. So this is the same of this one. And because of a VG bias here, although we don't directly bias in this region, but we bias on top. So therefore this VG versus the source actually still make this as a kind of like the forward bias. So we can start to expect the electron can diffuse into the channel. So once the electrons are diffused into the channel, we'll reach to this point. And just think about how we explain the MOSFET. We also mentioned the same themes that at this moment, how the electron can reach to the drain side because of the help of the electric field. And therefore, our electron carrier can stop to reach to the drain side and become the current here. So if you try to compare the operation of this one, because normally this plot is a little bit scary, that it's difficult to understand if you are the first time try to understand the BJT. But if you try to side by side compare with what we have explained in the MOSFET in this region, then probably this will help to understand that this graph, although it looks a little bit complicated, but the operation physics is the same. First of all, in the MOSFET, we apply the reverse large VD, so we will have a reverse bias here. And then also the electron can start to diffuse into the channel. And one thing is particularly interesting, you can see that why the channel is become triangular and then disappear at this region. This is exactly the same what I mentioned here. At the edge of the depletion region, the minority carrier should approach to the zero. So this disappear or reach at a certain point and then become zero afterwards also suggests that our concentration here should be approached to zero. So you will find out that this is exactly also illustrate the same concept here. So once we have electron diffused into reach this point, and then because of the reverse bias, we have a large electric field, so the electron can be swept and then in the end to reach to the drain side, so which is exactly the same like the bipolar junction transistor. So my point is just want to help that everyone understand that in the end you will figure out that why we learn the PN junction, because in the end we will see the real the real influence of PN in a transistor, no matter in the MOSFET or in the BJT, and then why we would consider the BJT operation and MOSFET, and then if you try to think about, then you will figure out that actually the operation physics are very similar, although the device structure not the same. But the most critical is we still have this NPN junction. We still have this NPN in the MOSFET structures here. Okay, so then we will start. So we have already in here we finally figure out how the carrier, the electron can transport in the BJT under this forward and reverse between the different junction. The next stage is for sure in the end we still need to derive some equations here. We want to use the equation to prove our understanding is correct or not. So we are interested in calculating currents in the bipolar transistor, as that in simple PN junction are determined by a minority carrier. So then we borrow the concept that we have already talked about, that once you consider the PN junction, everything is determined by the minority carrier. So therefore, if we want to determine the current in the BJT, we're also starting from the consideration of a minority carriers. So here is a sum of the definition for the loss of turns, and you can reference this later. So in the forward active mode, the B junction is forward bias and BC is reverse bias. And as there are two N regions, so we have a minority carrier host in both emitter and collector. So this is right. So because of this is N and N in these two regions, and for sure the hosts are minority carrier. So which is a minority host here, and this is our minority host. So as these are two N regions, so we have the minority carrier host. Are both in emitter and collector. And next step is that we were starting from the sum of the equation we have been already used. Now we use here again. So once we consider the base region, the steady state, it says minority carrier electron concentration is found from where we have already discussed that the bipolar transport equation, and therefore so we have this equation. So where NB it says minority carrier concentration in the base region, and dB and tau B are the minority carrier diffusion coefficient and lifetime in base region. So now we focus on this region, because in this region, minority carriers are the electrons. So the excess electron concentrations can be calculated by here. That's similar what we have been discussed in the previous chapter when we talk about the excess concentration, and then the general solution can be found here, and then the LB is a minority carrier diffusion length in the base. So furthermore, we start trying to solve this equation, and then we put the boundary condition here. So there are several boundary conditions here at the x equal to 0, and then the x equal to xb, and the Bipolar junction is followed by. So found the boundary condition at the x equal to 0 will be this, and then the BC junction is reversed by. So the second boundary condition is shown here, and then with this boundary condition, so finally we can try to solve the coefficient of A and B, and it then lead to the final solution for this equation shown here. And also we will try to move on to the emitter region. So the minority carrier hole concentration in the emitter can be expressed as below, where dE second derivative minus as shown here. So we have this minority carrier hole concentration in the emitter. And then similarly, we put this is a excess hole concentration general solution. We put a boundary condition. In the end, we have the formula shown here. Next will be the collector region. So in the case with the collector, so we doing the same. We're doing the same with considering exactly the same equation. So then we will, in the end, with considering this boundary condition, so we can try to solve this one. So finally, here is a summary. So finally, we have this equation, these three equations in all these three regions, which is the base region, emitter region, and then collector region, and then which, if you try to plot this in this minority distribution plot, in the end you will get the same result where I draw, where we explained before. So that's a equation. So finally, we can also prove our understanding by using this equation. So, but actually more important is what this equation implication and then the application. So, of course, as I say that personally, I'm not fully focused on the equation. I'm more focused on the physics behind, and then focus on how we can use this equation help us to design transistor or understand the physics. So therefore, we have tried to play a little bit about this equation and then try to derive some more interesting term here. And the next one, which is very important, is what we call the current gain. So in here, we will try to describe the transistor current and low frequency. That's what typically call the common base current gain. So the basic principle operation of bipolar transistor is to control the collector current by the base and emitter voltage here. So this one, so we try to control the collector current with the difference of the base and emitter voltage. Where is the base? This is base and this is emitter. So then the VBE is very important. So the collector current is a function of the number of majority carrier reach the collector after being injected from the emitter across the BE junction. So the collector, as I say, the collector current here is determined by the electron injected to the base in there to reach to the collector side. So this is what this sentence means here. And therefore, we can define the common base current gain, which is a ratio between the collector current versus the emitter current, which is as shown here. Collector current versus the emitter current. That's what we call this is alpha, which is a common base current gain. So therefore, we are interested in this is the emitter current here. So we are interested in the ratio which IC over IE is equal to alpha. So that's a common base current gain. Also, we are interested in another one that we call the common emitter current gain, where IC over IB is defined as a beta. So in here, we are interested in these two current ratio, where we define as a IC over IB here. So actually, the concept for the current gain in the BJT is not exactly the new concept. In the MOSFET, we are also try to consider the current gain, but in that moment we don't call the current gain. Actually, we call the transconductance. So now again, if you try to look back for the MOSFET, so in the MOSFET we have, this is a typical MOS transistor circuit symbol where we apply the VG, we ground it, and then we try to measure the drain current. So this is a typical MOSFET circuit symbol. But actually, we have already talked about in previous lecture when we discuss the MOSFET, there's a very important parameter that we call the transconductance. So the transconductance is actually considering this one. So that's a drain current versus the gate bias here. So in this case, actually, what we try to derive for the MOSFET is also the certain of the current gain, but it is with the ratio of a bias here. But now we just have a ratio between the current with IC over IE or IC over IB. So ideally, these two concepts are very similar, but just due to the different operation of the device, so we will have the different definitions. So once we have the equation for the current gain, then next stage we want to understand that which current is actually has a good contribution for this current gain. So the next one is we will try to talk about this in a little deeper, try to understand the contributing factors here. So then again, if you try to consider the BJT here, so we can draw the schematic of the BJT where we have the three terminal, that is emitter, that is base, that is collector here. And in here we consider the case of N, P, N, and therefore each junction has its own depletion ridge, has its own space charge width here. So then the first one is that there's a term called J minus NE. It's an electron injected from the emitter to the base, so which is this one. So first of all, we have this J minus NE, which is our electron flux injected from emitter to the base one. And as the electron diffuse across the base, a few will recombine with the majority holes here. So the majority carrier hole that are lost by recombine must be replaced from the base terminal. And this replaced hole flux is denoted by J plus RB. So this is a J plus RB as shown here. And also, once the electrons flux reach the collector, that will become the J minus NC. Which is this one. And the majority carrier hole from base region are injected back into emitter, results in a hole flux that we call the J plus PE. So we also have this hole injected back. So this is a J plus PE. Some electrons and holes are injected into a forward BE space charge region and will have a recombine in this region, and this recombine leads to the JR minus, which is this one. So generation of electron holes occur in the reverse BC junction. So this generation will yield the whole flux of a JG prime. So So we will have the generations in the base, which is this one, Zg plus here. And finally, the ideal reverse saturation BC junction is denoted as a JPC0, which is this one. So these are all the contributing factor for the current that we have in the bipolar junction transistor here. So with help for this, with analysis of this contributing current, so finally we will start to consider how to go further details to understand our current gain. So here is some more detail. Actually, this is exactly the same graph that where I already shown in the last slide. And then the next is more important. So now we can try to separate our overall current with collected in the collector side, or we have in the emitter side. So now we consider the alpha as shown here. And this will be equal to lots of the terms that are considered together. First of all, the IC is actually equal to the current in the collector, which is the one that we mentioned here, JNC. And then, but for the IE, it's a different. So IE has a different contribution factor, which we need to both consider the JNE and also the JR and also the JPE. So basically, we just try to summarize all of the current we can have in the emitter, which is include this JNE, JR, and JPE together. That would be the current in the emitter side. And then the current in the collector will be only the JNC here. So with this equation, then we can further try to expand expand this equation with some mathematical tricks where the alpha can be expressed again with considering this one. So now we can rewrite our alpha equal to these three. And why we can do this? The idea is very simple. Now we have the equation here. So if you try to consider the equation like in this way, and then you can figure out this equation. These two equations are exactly the same because of this and this can be cancelled, right? And this can be cancelled. So in the end, the equation here is only the remaining part. It's only this one and this one. And this is exactly equal to this one. But why we have to consider, why we have to expand the one simple equation to the three, because we want to give them a more physical based understanding. So now we can define this one as a gamma, which is equal to this one. And that's we call the emitter injection efficiency. And then the middle term is we call the alpha T. Which we call this as a base transport factor. And then last one is we call the delta, which is this one. Which we call this as a recombination factor. So again, then we can start to further come back to look at the equation. What does this equation mean? The first one is emitter injection efficiency. Actually, what we try to calculate is this one, the gamma, which is Jn Ne over Jne plus Jpe, which actually we try to calculate the ratio of this one versus this one. So that's why we call this as an emitter injection efficiency, because we want to understand how the Jne plus Jp is the total current, but we want to understand how much actually the Jne can be injected from the emitter to the base. So that's why we have this equation. And again, the next one is a base transport factor, which we actually try to calculate the ratio between this one and also this one. So the alpha T is equal to Jnc over Jne. So we actually want to calculate the ratio of this versus this. So from graph, now it's getting clearly, because actually we just try to understand the ratio of this current once reached to the collector side versus the one being injected from the emitter side. So that's why we call this as a base transport factor. And then the last one is a recombination factor. So where the equation here, so we have these three, and then the purpose is just trying to understand the influence of the JR, where we have already shown here. So now again, just try not to be confused by this equation, because in the beginning probably you will be very surprised that why we have to expand this, the simple one, to more complex one. But because of by expand the simple one, which consider as a whole equation that as a multiple by this, and this, that give us a higher physics-based sense that what we can use for this equation, because now we can understand each one has one particular meaning. Like this one, where is the emitter injection efficiency, and actually we want to understand the current reach to the emitter side over the overall current here, the current reach to the base side, which is this one, injected from the emitter side, overall the all current here. And then the alpha T is actually try to consider the current reach to the collector versus the current from the emitter. And then the last one, we have another consideration of the JR. Then we can understand the influence of the JR. So finally, we have more confidence about try to understand the current gain by consider 3 different terms, and each term has its own physics-based sense right now. Okay. So now we will further try to bring the equation we have and then try to derive more. And here is just mainly the formula calculations. So we have this gamma where we have defined, and then we can put this all the equation in the end, which will be this one. So with this one, finally, it will get some more practical sense for us, because we know the gamma factor is highly related to the different transistor design parameter, especially related to the base, and then related to your emitter, and then related to your base width, base concentration, emitter concentration, emitter width. So that means we can start to think about how to fine-tune these 4 parameters to have a different gamma. And similarly, if we consider the base transport factor, then we have this equation shown here. And then we have a recombination factor, then we have this one. So in the end, we have a summary of the equation that can help us to determine the overall current gain. So we have this emitter injection efficiency, we have a base transport, we have a recombination, and by putting all these equations, then we can get the full equation for this common base current gain and common emitter current gain here. And the one thing we need to further consider is that now we have the base collector and also the emitter here, and then actually the emitter is equal to the base plus the collector. So we consider this equation can be further derived here, and we also already define this will be equal to the 1 over alpha 0, and this will be equal to the 1 over beta 0, and therefore we have the formula to transform between the alpha and beta as shown here. But another very important, if we look closely for the common emitter current gain as shown here. So then actually how we increase the beta. Beta is always the most important parameter for us in the BJT. So if we want to design the BJT with a high current gain, So what we can do is first to decrease the base width or increase the emitter concentration. So then the typical design strategy to make a good BJT that has a high current gain. So what we usually do will increase NE, and second, we will decrease base width. So this is actually the most important conclusion. That's why we spend the time to derive the equation, because in the beginning, if you just purely look at the current gain equation, it's difficult to understand how we can further doing the optimize. And then therefore we split 1 into 3, and we consider 3 as a different contributing factor, and we put our equation inside for each 3. In the end, we have a more dimension-based or the concentration-based equation that allow us to do the optimization aside. So therefore, the beta show me here, where we can clearly understand what actually the impact of the change for each concentration or the space that will influence our current gain here. And with this equation and then with this strategy, then we know how to increase our current gain. But if you come back, look again, what's the implication of this design strategy? You will find out that this is very consistent for what we already mentioned before. For example, decrease XB. Decrease XB, that means we have a decreased base width. But why in the BJT we have a decreased base width? This is because we already mentioned before, we want to have a high gradient in this region, right? We want to have a high gradient of a minority concentration. So if we can make this XB smaller, of course, that will suggest our gradient is higher. And gradient is higher, is larger. That's good for diffusion current. Then we get the better current gain. So then you will see that actually what the equation try to tell us is already inside the physics-based explanation as shown me here. So that's why that this base width in the end will determine the diffusion current, and in the end will determine the base the current gain. And another is emitter concentration. Of course, the emitter concentration is a concentration here. Of course, larger NE, we can expect under the forward bias, more carrier can be flowed from emitter to the base. So in the end, this equation is a pretty physically makes sense, and then that's very consistent with what we already explained in this minority carrier plot. So there are several non-ideal effects here that we will talk about. The first one is a base width modulation. So if you consider the base width modulation is better, you can come back to look again. For the MOSFET, we have also similar effect, but we call the channel length modulation. So as we increase the BC, actually we knew that the base width is a function of the BC voltage. So the base width will be influenced by this reverse bias, because of this reverse bias will in the end influence our depletion width, and in the end will influence our BC width, base width. Since the width of space charge region extending into a base region with a BC voltage, as the BC reverse bias voltage increase, the base space charge region width increase, which will reduce XB. So this can be easily understood with a plot here. So we have the X to 0 here, and then we have the boundary of our space charge width, and then if we increase our reverse bias of BC, then our depletion width will extend. So this is due to the increase of BC space charge region. And this actually in the end will influence our minority carrier minority concentration gradient. So then this will become so the minority carrier minority concentration gradient increase. So a reduction in base width will cause a gradient increase, and then in the end cause the increase in the diffusion current. So now if you can follow what we have already discussed, how this the gradient in the end will cause the diffusion current, I think for here the base width modulation, it should be very clearly for everyone, because it's just a matter with in the end that the base will be highly influenced by our BC junction. So now we get a narrow base, and for sure our gradients become larger. So in the end, this will have the result of a current increase. And then also we can try to do the linear extrapolation. Then we have this VA, which is our early voltage, as shown here. So that's our early voltage shown here. So this is very similar to our channel length modulation in the MOSFET. Because in the MOSFET also, once our channel length decrease, we also see the similar IDVD will increase. The next one is a high injection. So in the previous, we always talk about, we consider everything is under the low level injection. But in reality, it is possible that we will have a high level injection. So then we also have to include the consideration of the high level injection. So this is happen if we consider the one BJT here, and we have the emitter, we have a base, we have a collector, which is NPN. So once our VBE is increased, then we can foresee that the electrons here can have the increase of the amount will try to flow from emitter to the base, right? And in this case, it might have the situation that our injecting electron can larger than the majority of the in the P region, which is Na. So this is Na, which should be the majority in the base, which is a hole. But now because of we increase our bias, and then there's a chance that the injected electron can exceed the majority of the holes, and that will trigger the issue of the high level injection. So this is actually, this one is suggest for this. So this is in the P base region. So that's an emitter, that's a collector here, and then we have a huge amount of electron is being injected here, and there's a chance that the background doping for NB is here, and then the injected electron in the end exceed the NB. So the Na here is the NB. So then we start to consider this as the high level injection. So as BB increase, the injected minority carrier concentration may approach or even become larger than the majority carrier concentration. And then now we have to assume there is what we call the quasi-charge neutralities here. So in the case of a quasi-charge neutrality, so we still, in the end, the overall system will maintain the neutrality, which means that the electron and hole should be in a certain balance. Now we have additional electrons. So this additional electron will also cause the additional holes. So considering this quasi-charge neutrality, then the majority carrier hole concentration in the P base will increase because of the excess holes. Which is here. This one. So original hole concentration is flat. Because of a high level injection, now we have additional electrons exceed our NB. So to have this quasi-charge neutrality, the holes will be increased as well. So now we have the excess hole. So the hole concentration will increase to maintain the quasi-charge neutrality. So this is minority and majority carrier concentration under low and high, and then the high level is the one with a dashed line. Of course, there are lots of equation further can be derived. What would be the influence of the high level injection in the BJT? But then the conclusion is that the current, this is typical current gain versus our collector current plot, and then we will start to see this is the case under the high level injection where our current gain is decreased, which is something that we don't want, because we always, when we consider the BJT, the first priority is to make sure we have a high current gain. But now we figure out that if we try to operate in the large VB, then our current gains decrease. So this is mainly due to the high level injection. So the two effects can occur in the transistor under the high injection. The first one is that the random reduction in the emitter injection efficiency. Since the majority carrier hole concentration at x equal to 0 increase with a high injection, more holes are injecting back into the emitter because of this 4B voltage here. An increase in the hole injection can cause the increase in the JPE current, and the increase of JPE can reduce the emitter injection efficiency, because now our hole concentration here become larger, so that means our JPE is increased. So JPE is in this direction, flow to the left will increase, and then the JPE increase that will influence our emitter, this one. So this increase due to the high level injection, and then this will cause a decrease of a gamma, and the cause of decreased gamma in the end cause the reduction of the current gap. So JP is here. It's a 1. We already illustrated before. So finally, with this one, then we will start to see how this will influence our IV curve here. So this is a typical case under the high injection effect, where our current start to decrease because of our current gain decrease. And this is exactly the same when we talk about the PN junction. So when we talk about PN junction, we also identify there's a high level injection where our factors in the bottom will become 2, and in the end that will cause our current decrease here. So another non-ideal effect in the BJT is what we call the current crowding here. So if you try to look at the typical case for the BJT, we have already mentioned that this is a real situation, how we try to fabricate the BJT here. Then we will easily to figure out that there will be huge current crowding at the edge, and then the current is difficult to flow to the middle side. So this is how we call the current crowding effect. And then how we try to solve this issue is we just try to have lots of small emitter inside the base, and then once we have lots of a small emitter inside the base, then we can get the more uniform current distribution. And this, based on this concept, we have to design the layout like in this one. So then you will see between the base and base and base, we have lots of emitter finger here, and this is try to reduce the current crowding effect. Also, when we talk about the BJT, we also have to consider the breakdown voltage. So because right now we have the 2 junctions, so then we may consider that the breakdown from the different junction, and also there are the different mechanisms. So there are 2 breakdown mechanisms that need to consider in the BJT. The first is called the punch through. So we actually already mentioned in the MOSFET, but that will also certainly happen in the BJT as well. So if you try to look at the schematic of the BJT, we have the E, B, C here. And then, first of all, inside the EB, there's already has a depletion width. And then inside the BC, also, there is a depletion width. And once we start have the reverse bias, in BC, then for sure the depletion width can start extend. So we might have the depletion width in this. Or further, where the depletion width can be expanded. So in this case, the depletion width from the BC can touch to the depletion width in the EB. Therefore, it is possible for the BC depletion region to penetrate completely through base region and reach the BE space region, and this is what we call the punch-through effect, which is this one. So, if you look at the MOSFET, exactly, we already mentioned, but now we can quickly go through again. In the MOSFET, source drain, gate. So we all know that we will increase the VD bias, and therefore the depletion width here is extend. And then this is and then this has a chance to have this punch-through effect. So the depletion width can extend to the source region and connect together. That's what we call the punch-through effect. So this is exactly the same because we have this NPN here. We have this NPN here. And also, we can look at from the Venn diagram that because of due to the punch-through effect here, the barrier of the E and B is very small. Then we have huge electric field here. So then the electron here can easily cross this barrier, reach to the other side. And this is because of due to the huge reverse bias. Which has a EF. Due to the huge reverse bias. So then this causes a punch-through effect that will cause a very high current. So that's one possible breakdown mechanism in the BJT. So here's some equation. Just to quickly go through. So we have this is a condition that reach for the punch through. So we put a VPT here, and this is VPT is equal to this one. This is NB. And also we have another one that we call the breakdown. That's a real breakdown due to the avalanche breakdown. That's due to the average breakdown. So, but in the case of the average breakdown, we have to consider that the different terminal, because now we have the NPN. So then we have the case. First, we call the BVCBO. Where we have NPN here. We have the emitter, collector, and base here. So the first breakdown is the breakdown between the base and collector. That's what we call the open emitter. Here we have the definition. That's what we call the BVCBO. So the BVCBO is a CB voltage breakdown in the case of the open emitter configuration. And then next one is this one. The same, but different. But now it's a open base. So we have a E, B, C, N, P, N. But now it's considered the breakdown voltage in the open base, where we try to characterize the breakdown voltage in between. That is a BVCO. So we have the two kind of different breakdown under the different bias case. And then if you try to schematically draw the breakdown voltage, which we have a collector, and then so we have the breakdown voltage schematically like in this way. First increase and then increase the breakdown. That's what we call the BVCO. So that's an open base. And then we have an open emitter, which has a roughly characteristic. That's a BVCBO. That's an open emitter. So and then the correlation between the BVCO and BVCBO is shown here. So finally, we finish all the very important concept for BJT. So we talk about how the device operation in the different mode. We talk about why we have a current under the forward active mode. And we discuss some of the equation. In the end, this equation gives us a hint that how we further optimize, especially for the current gain. And then also we talk about some non-ideal effect, which lots of cases that similarly we will observe the same things in the MOSFET. Even for the device operation, how the current can be generate and flow in the BJT. we also have a very high similarly like similar approach like the one we have the MOSFET. So now the next one is that we will also still have to share some of the basic circuit model, because this circuit model is important that if we want to do the modeling, then we will have a different kind of model, and this model are, to be honest, this model are very legendary model. This has been developed for the very long time, but in here I just quickly go through one of them, and then help you to have some ideas about what would be the possible circuit model for the BJT. So we have the three different model. One is the Ebers-Moore model, one is the Gamma-Poole model, and then one we have the hybrid pi model. And each model has several advantages and several disadvantages. So none of the model has the one that can be comparatively better than others. That would depend on our application. So in here, I just want to quickly show that the most important one is the Ebers-Moore model. So Ebers-Moore model is one of the classical model for the bipolar transistor. This particular model is based on interacting diode junction. It's capable in any of the transistor operation mode. So we have the schematic for the BJT. Then we can try to plot the model like in this way. So we have the emitter, we have the collector, we have the base here. Now we will divide by each junction, which is considering the diode and also the current source. So now in the one with between the E and B, so we have this one. So we try to put us a diode here because of for sure the BJT is just a combination of the diode. So we will put a diode here. That's represent for minus VBE here. And also because due to the turn on of this diode, we start to have a certain forward current IF. But we also need to consider the reverse current. Which is alpha R IR. So that's a left part for our model. And similarly, we have in the right, we have exactly the same. Where so in this case, we have the VBC I right in the left. And also the R5 IF. So that's a schematic for this Ebers-Moore model here. So we have the left hand side, we have the diode of the VBE that will have the IF, but also we consider the alpha IR here. And then also we have this one is IR, and then we consider the alpha IF which is here. So then this one IF is expressed here, and then the IR here. By the way, just revise that in the beginning I say the IR is reverse current. It's not reverse current, just a current between the right, and the IF is a current in the left here. And then one of the consideration is that this is IE plus IB plus IC is equal to 0. So in this case, even small, consider that all the current flow inside our junction. So in the end, the overall current plus together will be equal to 0. So that's an even small model. So finally, that will be the last one. Just want to share some of the recent results because of, as you already probably feel like the BJT, to be honest, is not that widely used. It's used for some of the application, but it's not widely used like our MOSFET. But still, there are some of the BJT in the different domains are very attractive. So for example, the BJT for the silicon carbide, because we want to make the transistor has a very high current gap. So this is a paper just to illustrate that the high current gap silicon carbide BJT here. And then again, we will try to look at the abstract first. So in the abstract, actually this paper is published in the IEEE deal, which is a very good journal in the device, semiconductor device research domain. But you can find out that the abstract here is actually very short, but it's already covered every important aspect. So the first sentence is always the key. The author report common emitter current gap beta of a 55 in the NPN silicon carbide bipolar transistor. So the reason why I want to put this reference as some additional explanation in this paper, just want to illustrate that the beta, the current gap, is a critical concern for the BJT. So we will start to see lots of literature try to explore the high current gap. Now we have been spend a lot of time discuss the beta. So now probably with look at this literature, you will get more sense about the importance of the beta, because the first sentence of this paper is just describe the beta. And then also the space between the P-base contact implant and the edge of the emitter finger is critical to abandon the high current gap. Also another I want to illustrate that the VCEO. This is the term we just talked about probably like 10 minutes ago. There's one we call the breakdown voltage in the diode or in the BJT, and the VCO is already mentioned, and VCBO. So this is also the very nice literature exactly to match our class, because of what we discussed in the class is exactly again appears in this publication where he described the beta, where we talk about the VCEO and VCBO. So now you can understand that in the BJT, beta and the breakdown voltage of these two are very critical. And then we can quickly look at for the introduction. So bipolar junction transistors are attractive for silicon carbide power switching device because of we don't have the critical gate oxide in the device structure, and the possibility of a conductive modulation, and nearly zero offset voltage. And now we see the important term, however. So however, BJT requires substantial drain current. So now again, this is equation we just talk about. Substantial drain current IB equal to IC over beta, and will dissipate additional on-state power, both of which are reduce the current gain. So again, the key term, the current gain. So now again, this is what we actually learned from this class. Is very useful because now you will see in the literature this term is coming again. And one of the important factors affect the current gain is a surface recombination, and this is a literature review to review the previous work. And the next critical term is in this work. In this work, we use a thermal oxidation process to have the produce a gate oxide in silicon carbide MOSFET to passivate surface, and the current gain around 55 is a higher reported today is observed in the forward characteristic. And then we study the recombination in induced defect. So that's the introduction. So from introduction, actually this introduction is deliver the same information just like the abstract, but the introduction also, the conclusion is also talking about the same things. So 4H silicon carbide BJT with a current gain of 55 are fabricated. So this is exactly to illustrate the same result. And also this one, the result of shows that current gain is limited by recombination and implant. So this is exactly the same sentence, but rephrase in the conclusion, and then because it is important result, so it has to be mentioned again to give a strong conclusions. So that's the paper for this one. So far we don't look at any experimental result, but we already understood what's the outcome of this paper. It must have the current gain characteristic. It must have the breakdown voltage characteristic. So now if you look at this one, yes, so exactly we will see that there's a current gain plot. This is exactly the current gain. We see this is beta versus different collector current. So already shown that the current gain usually will be reached in this way. But why will decrease? Because of the high level injection. So in the end, the current gain will still decrease here. Okay, great. So finally, we finish the BJT. So we'll take a break for 10 minutes and then we'll come back later. Okay, to save this time, so let's just continue. So the last part where we will discuss is another transistor that we call the JFET, which the full name is a junction FET. So it's a junction field effect transistor that we, in short name, we call the JFET, which is still important because in the lots of the domain, different application, different device technology, the JFET still considered is not exactly. Some of them they use exactly the same concept of JFET, but some of them they just a little bit slight revise. But the idea is very similar to this JFET. So the basic JFET we will use consider here is consider what we call the PN JFET here. So the idea is that we will try to have the transistor, but now we don't use P sub, we use N-type substrate, and we have the source. Again, similarly, we will have the source and drain. So that's a N plus for the source and drain. But the only difference compared to MOSFET is one, we use N sub. Another is we will intentionally implant P plus in this region as a gate. So then, actually, we will use this PN junction to control the channel. The channel. So that's a typical JFET operation. That's why you will see the schematic like in this way, that under the gate we have a P and P, and then the electron will try to flow through the N sub, reach to the drain, but it will mainly modulated by the PN junction here. So that's what we consider for the PN JFET operation. And why we call the junction FET, because here is a PN junction, here is a junction. That's why we call the JFET. So the operation for JFET ideally are very similar to the MOSFET here. And then, but the difference is that because we use N substrate, so the threshold voltage is negative. So the typical IDVG characteristic for the JFET is that the threshold voltage is below 0. So we have a characteristic like in here. So since the threshold voltage is below 0, so we consider this as a depletion mode device. Depletion mode device, because we need to deplete the channel. So therefore, at the VGS equal to 0 volt, here, the channel is already on. So then we give the VDS, so the electron can already flow, and then so therefore we have the current here. But now we need to pinch off. We need to switch off the device, so we give the negative bias here, so we can start to see the depletion region extend. The depletion region extend, that means our current decrease, our resistance increase, and finally at a certain moment VGS is equal to -2, and therefore we completely pinch of the channel. and therefore at this moment we won't have current anymore. So that's a typical operation for junction FET that at the VGS is equal to 0 volt, we already have a current, but we need to give the negative bias until a certain moment we pinch off channel, then we can switch off our transistor. And the same with the right now we only consider the influence of the gate bias, but we can also have to consider the influence of the drain bias. And once we have the influence of drain bias, then the VDS, this is a VDS increase, as shown me here. So the VDS increase. So the VDS increase will also make the device work in the saturation region as shown in here. Reverse bias increase, and then therefore you so that's a reverse bias. That's a actually we should not call reverse. We should call drain bias increase. And the drain bias increase will also extend the drain side drift region, and then deplete the channel only in the drain side, and that will also cause the saturation region. So following the concept of the JFET, then we have another one that we call the MOSFET. But now the MOSFET here is that we don't use as a PN junction as a gate, and actually we use a metal. We use a Schottky barrier metals, Schottky metal on top of the channel region. So the device structure is look like in this way. We have a source, we have a drain, we have the substrate here, and now we apply the we will not use the implant P. We just put a simple metal. But this is Schottky. We will put metal, but we don't form the ohmic junction. We form the Schottky junction. So this will be the Schottky junction also has a characteristic that the Schottky junction will form the depletion region. So therefore we can expect the modulation of this gate voltage can also cause the depletion region. So in the beginning, this is a depletion region which is larger than the channel, but now we apply the positive bias, then the depletion region is smaller. So smaller, that means you have the electron can flow to the left here. So now, because of the depletion width is reduced, and so your electron can flow. So that's also another type of a junction FET, but now we use the metal, and therefore we change the name as a metal, as a MOSFET here. And with following the same concept for MOSFET, that also lead to another very similar one that we call the high electron mobility transistor, which is a HENT. structure. In lots of the 3-5 base transistor, we always have this kind of a hand structure for the transistor operation, and this is because of that it's sometimes difficult to form the dielectric, but with this the hand structure we can actually have the very good electron. So that's actually the case as shown here. This is a case happening between the aluminum gallium arsenide and gallium arsenide hand device, and where in this case you will find out that in a certain region, in here we won't talk about the detail, but just some very interesting, a little bit magic physics. In the end, this will create a certain quantum well in this region, and most important is that in this region our conduction band is below our Fermi energy. So we all already knew once our Fermi level close to conduction band, then we become the N-type. But what would be the case if our Fermi energy above our conduction band? We have talked about one case before, which is what we call the degenerate semiconductor. So basically, it's become like a metal, because now you have the conduction band, but your Fermi energy is already above your conduction band. So you can imagine now it's trying to have the characteristic like the metal, and then this is the same one that we talk about in the really beginning. We talk about one type that we call the degenerate semiconductor. So that means at this region we have a lot of electron in the channel, and then it works become like cannot say become exactly like the metal, but it can be said that you will try to approach to the conductivity as good as a metal, but for sure in the end can still not be the same like a metal. But anyhow, we have the high electron concentration in this channel, and therefore this high electron concentration is way too high. So now in this case we give the very particular name. We are not only call this electron, we call this as an electron gas, because the gas, as you know from high school chemistry, already know that gas is a lot of a molecule try to concentrate in the one small region, and then it becomes a gas. So then we follow the same concept that we found this is the high concentration electron very crowded in the small region. And why is a small region? Because we have the quantum well here. So we call this as an electron gas. But another interesting thing is that if you look at this band diagram and then think about in the 3 dimension, where we have the X, Y, and Z, and we have a Y toward the top, we have X to the right, and we have a Z which is in the direction of the to our projector. So then you will find out that in this case, because of the quantum well, there's no possible that the electron can be flow toward the X direction, because right now electrons are highly confined by this barrier and this barrier. So it's difficult for electron flow to the X direction. So that means the electron is difficult to flow to the left, to the right. It's not possible. So right now, the 3-dimension electron flow reduced as a 2-dimension electron flow. So that's why, in this case, we call this as a 2-dimensional electron gas. So then you will very often to hear about once we talk about the hand, always there's since what we call the two-dimensional electron gas, which in the short name is called the 2-deck, which the 2-deck becomes the hands as a very amazing transistor because we have very high mobility and can be confined in a certain dimension here. So the 2D here means that we have the higher density, but only in the Z and Y direction. So because of this feature, that's why we have called this as a high electron mobility transistor. So that's why this name is coming out as a hand structure. And this is some of the basic the schema. This is a full schematic for the gallium arsenide. That we have the several very complicated dope and undope. Then I won't talk in the detail. But another very important is not only we will have the gallium arsenide has this kind of things, just like I say for the lots of 3,5 has a similar phenomena. And another very important one is what we call the gallium nitride. That's aluminum gallium nitride over on top of a gallium nitride. And in here, if you look at the gallium nitride Venn diagram, then you will find out that due to some very magic physics, in the end, we also has this kind of the Venn diagram where our EF is above our EC at a certain point. That's we call this is a 2D EG here. That's we have the 2D EG here. That's we have the 2D EG here. So here is a high electron mobility transistor, and then this is a full device schematic in the case of the gallium arsenide. So as I say that we have the huge two-dimensional electron gas in the channel. That's a 2-deck here, and then the operation is very simple. Because the 2-deck is already formed without any particular process. So ideally, at the VG equal to 0 volt, and you give the certain positive bias, then the electrons is able to flow to here, to here. So if you look at the characteristic for the IDVG here, at the 0, we already have the current. So this is what we call the normally on or depletion mode transistor. So at the VG 0 volt, we already have the current. But the problem is that how do we switch off? So if we want to switch off, then we have to apply the minus VG. And similarly, because we have the Schottky contact in this one, and then we apply the minus gate bias, then we will extend our depletion region. So our depletion region will further extend, and this is our depletion region. So that once our depletion region is deplete our 2-deck, then we won't have the current anymore. So therefore, the typical characteristic for the hand structure is that we have the threshold voltage is below 0, as shown here. But so that's why we put this as the same concept like the JFET, because of we have this already conducting channel, and we need to consider how to use the depletion to turn off our transistor. Okay, So in here, we just quickly overview the JFET here, and then we won't talk too much detail because that's already lots of things for everyone has to study. So let's talk a little bit more about the final exam. So just a reminder that we will have the 2 exams, and then that will have the midterm and the final, and in the end the grade is divided by equal. So then the score, the ratio between the midterm and the final is exactly the same, but the overall will be the 75, so which will be the 37.5 for each one. So that means if you did a good job, if you didn't do the good job for the midterm, you still have a chance in the final. And then we have a homework, we have a attendance. So basically for me, I think the homework and the attendance is a free score for everyone. I think for this semester, I only checked everyone. I think probably like 3 times, only 3 or 2 times. But the one I don't check, I consider everyone is coming. So for example, if in this semester, we have probably like 15, 14 lectures. So I only check the 2 or 3, but the rest of I consider that everyone is participating. So to be honest, it's a free score for everyone. Okay, and then this is some more detail. So we will start the exam on this Thursday and then 6:30. So we will finish the exam at 8 p.m. And then please come to a classroom by the 6:20 p.m. And then the classroom will be the next one, not this one, because on Thursday evening there will be another conflict with the class. So I borrow the next classroom. And this is open book exam. So some students try to reach me, ask that what kind of things they can bring. And then my idea is that you can bring everything, what you want. Slide, iPad, Excel, notebook, whatever you feel like that would be helpful for you. But just a reminder that the more things you bring, probably you will get more trouble because you are not familiar. You should be familiar with, and then bring the only things you feel like the most important. If you spend the time on the internet, I'm afraid that you won't be able to solve the question very efficiently. And then in here we have the slide 1 to slide 30 up to the BJT, that where we don't we will not include the JFET. We only have the exam up to the BJT, but it's everything. So we have a 60% from homework and the example, and also the calculator is needed. It's definitely calculator is needed. But if you feel like you want to use a laptop, that's still fine with me. But you need to make sure that your laptop has a good enough battery. Otherwise, you have to come here to find a place you can charge it, because usually in the classroom we don't have so many charging plug that you can use. So this is things for the exam. Okay, so finally we come to the midterm. So first of all, we have quite a huge of students here. So that's why that we cannot finish the grading immediately. But our TA is working very hard because they have to grade the homework, also grade the midterm exam here. So due to the time, so we won't talk too much for how to solve the midterm question. I have already uploaded this in the E3. You can check it. So I will just distribute the midterm result to everyone, and then if you have any question, the TA is here. You can check with him. So I will probably in here I will just stop the recording.